Before you start using the bench grinder, it's vital that you set it up correctly. When operating, the abrasive wheel turns at high speed and produces dangerous and hot flying particles and sparks. Make sure the grinder is both switched off and disconnected from the power supply before you attempt to adjust it. Certain safety attachments must be in place before operating the grinder. They are the wheel guard, the see-through safety shield, the tool rest, a water pot, and a full face protector. The grinder may have abrasive grinding wheels for removing metal, a wire wheel to clean parts, or both. Make sure the wheel you're using is appropriate for the job. With the correct wheel fitted to the grinder, adjust the tool rest. Position it so there's at least 1/16 of an inch gap between the wheel and the tool rest, and that it is the same height as the center of the wheel. To adjust the tool rest, locate the adjusting bolt and loosen it with a box wrench. Set the tool rest at the right height and distance from the wheel, and then tighten the adjusting bolt. If you are unsure of how to do this, ask your supervisor. Connect the grinder to the power supply. Adjust your face protector, stand to the side of the wheel, and switch the grinder on. Once the grinder is up to speed, move to the front of the wheel. Hold the part firmly onto the tool rest and move it slowly and gently forward until it comes into contact with the wheel. The grinding wheel removes the metal it contacts. Occasionally, dip the part into the water to keep it cool. When you have finished, turn off the power and unplug the grinder. Disc brake pads consist of friction material bonded onto a steel backing plate. The backing plate has lugs that locate the pad in the correct position in relation to the disc. Calipers are usually designed so that the condition of the pads can be checked easily once the wheel has been removed, and to allow the pads to be replaced with a minimum of disassembly. Some pads have a groove cut into the friction surface. The depth of this groove is set, so when it can no longer be seen, the pad should be replaced. Some pads have a wire in the friction material at the minimum wear thickness. When the pad wears to this minimum thickness, the wire touches the disc as the brakes are applied. A warning light then tells the driver the disc pads are due for replacement. The composition of the friction material affects brake operation. Materials which provide good braking with low pedal pressures tend to lose efficiency when they get hot. This means the stopping distance will be increased. Materials which maintain a stable friction coefficient over a wide temperature range generally require higher pedal pressures to provide efficient braking. Warm up the transmission fluid by idling or driving the vehicle. Raise the vehicle and ensuring that it is level and stable. Do a visual inspection for leaks from the transmission. Most transaxles have drain plugs fitted to them that are easily accessible. However, some require that a housing be removed in order to drain the oil. Other types do not have drain plugs and require a suction pump to draw out the lubricant by hand from the filling point. Consult the shop manual for correct procedures for draining the fluid on the vehicle you are working on. Be careful because the lubricant can be hot enough to burn. Locate the position of the drain plug and remove any guard covers if necessary. Select the correct wrench and loosen the plug. Position a large diameter drain pan under the transmission. Clean the plug and then remove it. In the case of an automatic transmission, if there is no drain plug, loosen all the transmission pan bolts with the correct wrench and remove all but 3. The minimum necessary to hold the pan in place. Fluid will flow into the drain pan. Once the fluid stops flowing from the bolt holes, support the transmission pan with one hand and remove the remaining bolts to drain the remaining oil. Look for metal in the fluid, which looks like shiny particles or flakes. If the transmission has been overfilled during service, it could have caused internal damage to components. Also inspect the transmission pan and the residue in it. A small amount of metal deposits is normal, but a buildup could signal excessive transmission wear. If you find larger pieces of metal or clutch material that looks a lot like brake lining material in the case of an automatic transmission, have your supervisor come and inspect it. It is good practice to keep these larger particles in case the owner wants to see them. With an automatic transmission, carefully remove the oil pan gasket. Don't use a sharp tool that could damage the sealing surface. Clean the pan with a lint-free cloth and remove the transmission filter. Filters and screens may be held in place by several screws of varying sizes. Be careful to note any size differences of the screws so you can reinstall them in the correct position. If you have a paper or cotton filter in the transmission, it must be changed every time you change the transmission fluid. Metal filters can be cleaned with solvent or a spray cleaner and reused after air drying. Install the new filter on the valve body as described in the shop manual. Place the new gasket on the sealing surface of the fluid pan. Apply the manufacturer's recommended sealant to the gasket if needed. Replace the transmission or sump pan and tighten the bolts to the manufacturer's specified torque. Over-tightening the bolts may damage the gasket and/or the sealing surfaces. After the lubricant is completely drained, clean the drain plug. Put the drain plug back with a new washer. Use a torque wrench to make sure the torque is correct. Check the shop manual's lubrication guide for the correct replacement fluid specification and the correct quantity. If the filling location is under the hood, you will need to lower the vehicle. Clean the nozzle of a lubricant pump with a clean, lint-free rag or paper towel. Use the pump to put new transmission oil into the filler hole or dipstick tube opening. Pause for a few seconds after each pump to give the lubricant time to flow to the bottom. Stop when the lubricant reaches the bottom of the filler plug hole or to the top of the cold mark on the dipstick. In the case of an automatic transmission, start the engine. Apply the foot brake and move the transmission selector through all the gear selections. This will allow all the cavities in the transmission to fill with new fluid. Place the transmission in the correct gear for fluid checking. Check the new fluid level, adjust if necessary, and replace the dipstick or filler plug. Check the tension and condition of the belt around the compressor pulley. An air conditioning compressor uses quite a lot of power, so a loose belt or one glazed from slippage in the past may not be driving the compressor properly. Check the condenser to make sure that it is not clogged with mud or leaves, which will prevent it from radiating to the outside, the heat collected from the inside of the vehicle. The fins on the condenser can be cleaned with water and a stiff brush if necessary. Check that the flexible hoses to the various components of the air conditioning system are not cracked or soft or brittle, and that they are connected securely with no obvious signs of leakage or corrosion around the connections. Some of the hoses may be metal pipes. Check that these rigid lines are securely fixed in their routing positions and also look for signs of leakage at their connections. Some lubricating oil circulates with the refrigerant in an air conditioning system, so look for wet stains around all the hose connections, as well as around the gaskets on the compressor, as these may also indicate refrigerant leakage. Start the engine and then switch on the air conditioner. You should hear a firm click as the compressor clutch engages. Set the blower fan to high and check whether the air coming out of the vents inside the vehicle feels cool. Then switch the fan to its lowest setting and use a stem dial thermometer to compare the ambient temperature with the cooler air coming out of the air conditioning system. The difference should generally be around 20 degrees Fahrenheit or 11 degrees Celsius, although this will vary with different outside temperatures. Let the engine run at around 1500 RPM with the air conditioner on for 5 to 10 minutes. Then feel the hoses on each side of the compressor. The high side, or outlet hose of the compressor, should feel significantly hotter than the low side, or inlet hose. There are 3 anchor points on lap and sash type seat belts, and 2 on lap-only type seat belts. First, check the side anchor bolt that holds the buckle end in place. Make sure it is sound and secure. Next, check the security of the bolt on the retractor housing. This is usually located near the bottom of the door panel next to the seat. Above the retractor is the upper anchor bolt. These bolts are sometimes adjustable in a slider unit. Check that this is also secure. Examine the seatbelt material to see if there is any fraying or excessive wear. Check the seatbelt label for an expiry date. If the belt is past its use-by date, then report this to your supervisor, as the belt should be replaced. Pull the seatbelt out slowly to check for smooth action. There should not be any sticking, which might indicate a faulty retractor. Do this 3 times to make sure that it is consistently smooth in operation. Pull the seatbelt out quickly to see that it locks and releases. The belt should lock when pulled suddenly, which is vital during emergency braking or collisions. If the belt does not retract smoothly, remove the retractor housing and test it again. If the belt now retracts smoothly, then the retractor housing may need to be replaced. When the retractor is tilted beyond 45 degrees, the belt should remain locked. If the belt fails to function correctly, report it to your supervisor. Before removing the spark plug, disconnect the spark plug high-tension lead by grasping the boot where it connects to the plug. Twist it and pull it firmly straight out. If possible, use a small paintbrush to clean away any loose dirt or dust gathered around the base of the plug, which may fall into the cylinder when the plug has been removed. The correct tool to use is a spark plug socket. This usually has a rubber insert to protect the plug while it is being removed. Spark plugs can sometimes be difficult to remove, so you may need to extend the wrench handle for additional leverage. Turn the plug counterclockwise to loosen it, and then turn the socket by hand until you can remove it. Remove the spark plug from the socket and clean it, brushing away any light deposits with a wire brush. Check the condition of the plug. If the insulator is cracked, or the electrodes are burned or heavily corroded, or the thread is stripped, then the plug will need to be replaced. If the plug is dirty or oily, this may indicate a problem elsewhere, and you should report this to your supervisor. Check the plug specifications for the correct gap, and measure this with a wire gauge of the correct diameter. If the gap between the electrodes is too wide or too narrow, adjust it by bending the ground electrode with a gap adjusting tool. There are hundreds of different spark plugs, so make sure that any replacement you install has the correct code number for the type of vehicle you are servicing. Replace the spark plug in its seat, carefully screwing it in by hand to avoid stripping the thread. When the plug is finger tight, use a torque wrench to tighten the plug to the correct specification. Do not over-tighten, as this can damage the plug. Apply some silicone lubricant to the inside of the boot at the end of the coil lead and push it firmly into place over the exposed spark plug terminal. Start the engine to confirm that the plugs and leads are functioning correctly and that the engine is not misfiring. Make sure there is no power connected to any circuit that you test for continuity. Then, prepare the digital volt ohm meter, or DVOM, for testing voltage by inserting the black probe lead into the common input port and the red probe lead into the volt ohms input port. Turn the rotary dial of the DVOM to the mode that includes the term continuity. The digital display should now give you an out-of-limits reading, indicating that there is not a continuous circuit connection between the two probes. Touch the probe ends together. The display should now give a 0 reading, which indicates no resistance. This means that there is a continuous circuit through the probes. Some meters also indicate continuity with an audible tone. One typical use of the test is to determine whether a fuse needs to be replaced. If the fuse has been overloaded and blown, then it will no longer complete a circuit when a DVOM is used to test it. To check this, place the black probe on one end of the fuse and the red probe on the other. If the fuse is functioning correctly, then the reading will be 0, indicating a complete or closed circuit. If the fuse is open, then there will be no reading and no tone, indicating an incomplete or open circuit. A continuity test is used to check for a broken circuit caused by a break in a cable or lead, or caused by a component becoming disconnected. The same test can also confirm whether there is continuity between components which are not supposed to be connected. When this occurs, it is known as a short circuit. This test can also be used to check circuits that are suspected to have a high resistance. There are different types and sizes of wire terminals, but the procedure for installing all of them is the same. This is a bullet type of crimp terminal. Make sure you have the correct size of terminal for the wire to be terminated, and that the terminal has the correct volt-amp rating for the job it is to perform. Remove an appropriate amount of the protective insulation from the wire. Always use a proper stripping tool that is in good condition. You will get a better connection if you do not twist the strands together tightly before placing them through the terminal, as this gives the terminal more surface area to come in contact with the wires when crimped. However, it can be difficult to insert the wires into the terminal if they are all just loose strands, so twist them together just enough to help you insert them cleanly. Place the bullet or terminal onto the wire. It is important that the stripped part of the wire does not extend beyond the insulated part of the terminal. Some types of crimp terminals do not have an insulation component fixed to them. These come in two parts, and the insulator is supplied as a separate component. In these cases, always make sure that the core of the wire to be crimped extends through the core wings in the terminal. Use a proper crimping tool for pin or core crimping. Do not use pliers, as they have a tendency to cut through the connection, which can give trouble during service. Select the proper anvil for the connector or terminal selected. These are usually color-coded, so it is easy to match the terminal with the right size anvil. Crimp the core section first. Use firm pressure so that a good electrical contact will be made, but not excessive force, as this can bend the pin or terminal. Then crimp the insulation wings or section. This crimp is on the wire insulation to hold the cable in place, not for electrical contact, so you do not need to crimp this section quite as hard. Give a gentle tug on the finished job to ensure that the connection will hold in service.
What is a stroke? It's the movement of the piston from top dead center to bottom dead center. Calling an engine four-stroke means its engine cycle has 4 strokes. A 4-stroke gasoline engine uses internal combustion, so those 4 strokes must include the 5 key events common to all internal combustion engines: intake, compression, ignition, power, and exhaust. Let's look at a simplified model. The intake stroke starts with the exhaust valve closed, the inlet valve opening, and the piston at its highest point, top dead center. It starts to move down, increasing the volume above the top of the piston. This makes pressure inside the cylinder lower than pressure outside. This higher outside air pressure forces air-fuel mixture into the cylinder. The piston reaches bottom dead center, the inlet valve closes, and the intake stroke ends. Both valves stay closed as the piston leaves bottom dead center. The piston moves up, squeezing the air-fuel mixture into a smaller and smaller volume, which compresses it. That makes its temperature rise, and that makes combustion easier. Just before the piston reaches top dead center, the next key event occurs: ignition. Burning expanding gas generates the force to push down the piston. This is the power stroke that drives the engine. The piston now moves from bottom dead center to top dead center. The exhaust valve opens, and the piston pushes out the leftover gases. Let's look at the cycle operating. Intake takes in air-fuel mixture. Compression squeezes the air-fuel mixture into a smaller and smaller volume. Ignition. The mixture under pressure is burned. Power. Burning expanding gases push the piston down, creating a power stroke that turns the crankshaft. Exhaust. The piston moves upward, forcing burned gases from the chamber. All 5 events occur in this order in each of the engine cylinders.
Use a thread pitch gauge to confirm the size of the bolt or stud. This should match the thread it will go into. Choose the correct size and type of tap and die set for the job. It will be either inch or metric. Fit the die into the die stock, using the locating screw on the stock to engage the hole on the die and secure it into place. Apply a small amount of thread cutting compound to the exposed, damaged threads of the bolt. If the bolt or stud is a separate item, hold it upright in a vise. Make sure the vise is equipped with soft jaws so you don't damage the thread any further. Then tighten the vise so that the bolt is vertical. Slowly and carefully turn the die stock in a clockwise direction onto the damaged bolt. Make sure to keep the pressure vertically above the bolt. You will feel the die removing the metal from the bolt. Continue to turn the die until you reach the depth to which the matching nut will be tightened. To remove the die, turn the die stock counterclockwise up and away from the bolt. Clean any filings or particles from the cutting threads of the die. Use a rag and then a wire brush to clean the compound and metal particles from the thread of the bolt before you remove it from the vise. Test the job by using the correct size nut and tightening it by hand all the way down the bolt or rod. If the repair is sound, dismantle the die from the die stock, clean them both, and put them away safely.
The three interdependent factors in achieving a gasoline engine's full operating capacity are proper air-fuel mixture, proper compression, good combustion. The role of maintaining the proper air-fuel ratio is played by the fuel system. The two types of fuel systems are the traditional carburetor, which operates mechanically, and the electronic fuel injection system, or EFI, which uses a small computer to obtain the proper air-fuel ratio. Now let's look at the construction and operation of the carburetor. In this video, we will introduce the following 4 points. First, the components of the fuel system. Second, the principle of the carburetor operation and the importance of a proper air-fuel ratio. Third, the construction and function of the carburetor. And finally, the adjustment of the idle mixture. The fuel system is made up of the following components. The fuel tank, where the fuel is stored. The fuel filter for removing impurities. The fuel pump, which sends fuel under pressure to the carburetor. The carburetor, where air and fuel are mixed, atomized, and sent to the engine. The charcoal canister, which prevents gasoline vapors from escaping from the fuel tank. And the fuel lines, which connect the various components. The fuel inlet line and the fuel sender gauge are installed in the fuel tank. The fuel filter contains a filtering element to remove water and foreign matter from the fuel before it enters the engine. The fuel pump draws out fuel from the fuel tank and sends it under pressure to the carburetor. The diaphragm-type fuel pump shown here is the most common type of fuel pump used with carburetors. The diaphragm-type fuel pump of the 4AF engine is installed on the engine block and is driven by a cam on the engine's camshaft. The fuel pump has a diaphragm in it and a pair of valves which act in the opposite direction from each other. These valves are actuated by the reciprocating movement of the diaphragm and feed the fuel to the carburetor. The charcoal canister prevents the fuel vapor from escaping from the fuel tank. The canister is filled with activated charcoal. The vapor that passes through the charcoal is absorbed and combined with outside air, then sent to the combustion chamber where it is burned. The carburetor mixes the proper amount of air and fuel in accordance with the operating conditions of the engine and sends it to the combustion chamber. The principle behind this is similar to that of a manual paint sprayer. When air is blown through the pipe, The liquid inside is drawn up and mixed with the air, forming a spray. An increase in the speed of the air blown through the tube will create to draw up the liquid and create a mist. This is a model used to demonstrate the principle behind the carburetor. Air is blown in at the bottom, creating a vacuum which forces the liquid out. We will explain the functions of the carburetor using this model. First, we will conduct a test in which the nozzle of the fuel pipe alone protrudes into the air tube. If a vacuum is applied to the bottom of the tube, we see that the fuel rises in the pipe a little, but due to insufficient air pressure, enough fuel will not exit the pipe. Now, let's narrow down the mouth of the tube to speed up the airflow and see what happens when we try it again. As you can see, liquid is atomized, that is, changed into a mist that can be blown out through the pipe. This is basically how a carburetor works. The portion that was made narrower to speed up the airflow is called the venturi. Below the venturi is a throttle valve which controls the air-fuel mixture. It is connected to the accelerator pedal. These comprise the fundamentals of the carburetor. This is how the air and fuel are mixed, but it leaves us with one problem, namely how to achieve and maintain the proper mixture of air and fuel, or the correct air-fuel ratio. Theoretically, the optimum ratio for combustion is 14.7 parts of air for every 1 part fuel. If this theoretical ratio is achieved, the result will be easy engine starting and complete combustion. As long as a mixture at this ratio is supplied by the carburetor, the engine will run smoothly. Now let different driving conditions beginning from when the vehicle is started. Naturally, the engine is cold, making it harder for the fuel to be atomized. This alone is enough to create an improper air-fuel mixture. Hence, it is necessary to provide a greater ratio of fuel to air. Just when the vehicle is accelerating. We know that fuel is heavier than air, so since the amount of air is increased when the accelerator pedal is pressed, the amount of fuel also must be increased to obtain sudden acceleration. When the engine is idling, or when the vehicle is traveling at low speeds, fuel and air do not mix well. Because of this, it is necessary to achieve the theoretical ratio, or a slightly richer mixture. A greater ratio of fuel to air is necessary to obtain the needed power when climbing hills, or other times when the throttle valve is wide. The theoretical air-fuel ratio, or a slightly leaner mixture, is needed when driving on straight even roads at constant speeds. So as you can see, the carburetor must create the proper air-fuel mixture under a variety of driving conditions. Although there are many types of carburetors, we will examine the workings of the carburetor used for the 4AF engine. This carburetor is called the double barrel type because it has 2 passageways, or barrels, for carrying the air-fuel mixture. This is the primary barrel, and this is the secondary one. The air that passes through the air cleaner enters the barrels here. The fuel from the fuel pump enters the float chamber here. Next, let's look at the float system. The venturi determines the amount of fuel that is drawn in and mixed with the air. However, if there is any variation in the height of the nozzle from the fuel surface, labeled H in the diagram, there will be instability in the air-fuel mixture.
So, the float system was devised to maintain a stable level of fuel in the float chamber, which changes in the distance between the nozzle and the surface of the fuel. The float system consists of the float chamber, the float, and the needle valve. The air vent tube ensures that a uniform pressure is maintained in the float chamber and above the choke valve at all times. If the fuel level drops, the float will also drop, causing the needle valve to open and allow more fuel to enter the chamber. Conversely, if the level of fuel increases inside the chamber, the float will rise and close the needle valve, stopping the flow of fuel. The 4AF engine carburetor is provided with the variator to maintain the proper air-fuel mixture. Of these, only the primary barrel is used when the vehicle is traveling at low or medium speeds. Both the primary and secondary barrels are utilized. Let's look at these in order. The primary low-speed circuit supplies the air-fuel mixture when the vehicle is idling or traveling at low speeds. Here we will use a model to demonstrate. As you can see, the throttle valve opening is very small when the vehicle is idling or traveling at low speed. The amount of air allowed in by the venturi is small, insufficient to draw much fuel. Now let's place another port below the venturi and see what happens. Because the vacuum below the venturi is greater, more fuel is drawn into the barrel. This is the primary low-speed circuit. The actual flow of the fuel is as follows. It leaves the float chamber and passes through the main jet, then through the slow jet, which controls its volume. It then goes to the primary air leader, where it is mixed with air, and then to the economizer jet, where the volume is further controlled. Then the air from the primary air bleeder is mixed well with the fuel and delivered from the idle port. The idle port is supplied with an idle mixture adjusting screw to allow the idle air-fuel ratio to be adjusted. The mixture can be made richer while the engine is idling. When the throttle valve is opened slightly from the idle position, there will be an increase in airflow. However, the fuel supplied by the idle port alone would result in a lean mixture. To prevent this, there is another port called the slow port. The effective surface area of the slow port increases as the throttle valve opens. This prevents the mixture from becoming too lean until fuel can be delivered from the main nozzle. The fuel supply and slow port stops when the throttle valve opens to draw out fuel from the main nozzle. In the primary low-speed circuit, there is a fuel cutoff solenoid. When the ignition switch is off, the root is closed and the fuel supply is interrupted. In some engines, a fuel cutoff solenoid also activates when the engine is running at slow speeds. Next is the primary high-speed circuit. The construction of this is similar to that in the carburetor model we looked at earlier. It is the most widely used main circuit, although there are mechanisms to activate to assist when extra or speed is needed. This side is the primary barrel on this model. The venturi is designed this way for maximum mixing of air and fuel. The primary high-speed circuit works as follows. When the throttle valve is opened wide, allowing for a higher speed and volume of air to the venturi, the amount of fuel that is delivered is equivalent to the intake air volume drawn into the barrel. The amount of fuel is controlled at the main jet before it is mixed with the primary air bleeder and injected from the main nozzle.
The fuel is atomized by the air flowing at high speed past the venturi, from which it enters the combustion. This is how the air-fuel mixture is regulated during idling at low and medium speeds. However, this alone will not produce the power needed during high-speed operation. This is why the double-barrel carburetor has a secondary barrel. The construction of the secondary barrel is the same as that of the primary barrel. It has a high-speed circuit, which is its main circuit, and a low-speed circuit which prevents the mixture from becoming too lean when the throttle valve opening on the secondary side is small. Let's look at the secondary low-speed circuit for the secondary barrel. If the primary throttle valve opens more than 60 degrees, the cam in the kick-up system will force the secondary throttle valve to open slightly. And is then secondary slow port, causing fuel to be delivered to the intake manifold.
When this happens, the vacuum bleeder, which is part of the venturi, produces a vacuum which opens the secondary throttle valve. When the engine RPM rises, the pressure from the vacuum bleeder overcomes the diaphragm spring, which in turn causes the secondary throttle to slowly open. The secondary low-speed circuit, like the primary low-speed circuit, uses a solenoid so that when the ignition switch is off, the root is closed off. Now let's move on to the secondary high-speed circuit. When the secondary throttle valve starts to open, a vacuum is created by the vacuum bleeder. This is strengthened by the diaphragm, which causes the second throttle valve to open further. The fuel is injected from the secondary main nozzle. In this way, both the primary and secondary barrels work together to produce the air-fuel mixture necessary for high power. Now let's take a look at the power circuit. The high-speed function provides insufficient fuel when climbing steep grades or when extra pay. This power circuit comes into the picture. The power circuit consists of a power valve set into the root that communicates with the primary main jet. It opens to allow more fuel to flow through to provide the rich mixture needed when extra power is called for. When driving at a constant speed with the opening of the throttle valve small, the power valve is closed due to the high manifold pressure. When a big increase in power is needed, the driver depresses the accelerator pedal, thus opening the throttle valve wide. This causes a decrease in the manifold pressure. When the pressure in the manifold falls below the standard value, the spring pushes down the power piston and opens the power valve. The flow of fuel becomes less restricted and the fuel is delivered from the main nozzle. Now let's take a look at the acceleration pump. We all know that to achieve quick acceleration, the driver needs to depress the accelerator pedal suddenly. The acceleration circuit is designed to prevent engine hesitation during such sudden acceleration. With the pump-type power circuit, when the throttle valve is suddenly opened, the pump lever depresses the pump plunger. This increases the flow of fuel from the acceleration pump jet. Slowly releasing the accelerator pedal allows the pump plunger to rise to the usual position. This causes the fuel to be drawn up into the pump chamber, where it is held in reserve for the next time sudden acceleration is needed. There is also an auxiliary acceleration pump that assists the acceleration circuit when the engine is cold. When the engine coolant at a low temperature and the TVSV is open, the pressure from the intake manifold causes the diaphragm of the power assist pump to activate and fill the pump with fuel. If sudden acceleration is attempted at this point, since the pressure in the intake manifold falls, the diaphragm spring causes the fuel in the pump to be sprayed out of the nozzle.
In this way, the pump makes up for the lack of power in the main speed pump. This brings us to the choke system. Without a choke, it would be difficult to start the engine in cold weather. The choke valve is provided above the nozzle to decrease the amount of intake air during starting. In this way, the choke helps start the engine and improves drivability. The choke valve is located in the primary side air horn. At present, as is shown here, the most common type is the automatic choke system. We will also introduce the electric automatic choke, which is currently in use in most vehicles. The automatic choke is controlled by the contraction and expansion of a bimetal element. When the temperature falls below a set level, depressing and releasing the accelerator pedal will cause the choke to be completely closed by the contraction of the bimetal element. After the engine is started, current will flow through the electronic coil. This will generate heat, which will cause the bimetal element to expand and open the choke either slightly or all the way. Here we have the fast idle mechanism, which raises the engine idle speed when the temperature is cold in order to maintain proper engine operation. When starting the engine in cold weather, depressing the accelerator pedal once and then releasing it will cause the fast idle cam, which is connected to the choke valve by a rod, to open the throttle valve slightly. In this way, a slightly higher engine idle speed is achieved. After the engine is warmed up, it will continue to run at a fast idle, even if the choke valve opens, until the accelerator pedal is depressed again. When this happens, the cam follower rides up over the cam and the fast idle is released. This causes the throttle valve to return to the normal idle position and the engine speed to drop. Let's move on now to the unloader mechanism. The unloader prevents the air-fuel mixture from becoming too rich if the engine is started and runs cold without sufficient time given for warming it up. When the accelerator pedal is fully depressed, the throttle shaft arm moves the fast idle cam to force open the choke valve slightly. This allows more air to enter to prevent the mixture from becoming too rich. Let's look at the choke breaker. During cold starts, the choke valve may remain closed, providing an overly rich mixture, which could lead to engine stalling. The choke breaker causes the choke valve to open slightly in this situation to prevent the engine from stalling. When the engine is started, the low intake manifold pressure causes diaphragm A to slightly open the choke valve. After the engine warms up and the coolant temperature rises to normal operating temperature, the TVSV opens, and the vacuum from the intake manifold causes the choke opener diaphragm B to open. After this, the choke valve is operated by the auto choke mechanism. Now, let's see how to adjust the idle speed and mixture. You should use a CO meter to do this if possible. First, in order to adjust the speed mixture properly, we must make sure that the following conditions are met. Make sure that all the electrical accessories are turned off. Check to see that the transmission is in neutral. Make sure that the engine is warmed up. Confirm that the ignition is set properly. examine the float level in the carburetor to see if it indicates the correct fuel level. And finally, check to confirm that the choke valve is completely open. After these conditions have all been fulfilled, connect the engine tester and proceed to check the idle speed. Remember that the test must be done with the air cleaner in place. In some models with an air suction system, you move the air suction vacuum hose and plug it with a hose plug. Turn the idle mixture adjusting screw to raise the engine RPM to its highest permissible idle setting. Then turn the idle speed adjusting screw to set the idle to specify idle mix speed. Repeat these two steps until the engine RPM will no longer go above the highest permissible idle setting. Finally, turn the idle speed adjusting screw to set the idle speed to the specified setting. After this, rev the engine to about 2,000 RPMs for 30 to 60 seconds. Give the idle speed 1 to 3 minutes to stabilize, then test the exhaust by inserting the CO meter probe 3 centimeters or about 16 inches into the tailpipe. If the CO emissions are above standard, or if the engine is still running rough, repeat the previous steps and adjust the CO emissions with the idle mixture adjusting screw, as well as adjusting the idle speed with the idle speed adjusting screw. Next, we will see how to adjust these without the use of a CO meter. In model with an air suction hose to the air cleaner, remove it and plug the end with a hose plug. Turn the idle mixture adjusting screw to raise the engine RPM to its highest permissible idle setting. Then, turn the idle speed adjusting screw to set the idle to the specified idle mixture speed. Repeat these two steps until the engine RPM no longer go above the highest permissible idle setting. Finally, turn the idle mixture adjusting screw to set the idle speed to the specified setting. In this video, we have discussed the fuel system by focusing on the design and operation of the carburetor. The fuel system greatly affects the vehicle's operation, power output, and fuel efficiency. It is our sincere wish that this video, in connection with other training materials, will help you to understand the fuel system and be useful in your daily service operations.
The most widely used hydraulic shock absorber is the direct-acting telescopic type. It can be fitted as a self-contained unit or combined with a suspension strut. The strut type uses the same principle of operation, but it is considerably larger. The hydraulic shock absorber provides its dampening action by transferring oil under pressure through valves which restrict the oil flow. The twin tube type is the most common. The outer tube is normally attached to the suspension member at its base, and the inner tube provides a working cylinder for a piston which is attached to a piston rod. The piston rod is connected to the frame at its outer end, and a bearing at the top of the outer tube keeps the rod in alignment as it moves in and out of the shock absorber with suspension action. A seal above the bearing prevents oil leakage and keeps out dirt and moisture. A shroud protects the rod from damage. During bumps or compression, the rod and its piston move into the shock absorber. In rebound or extension, the rod and piston move out of the shock absorber. For dampening to be effective, resistance is needed in both directions. This is provided by the oil and by disc valves attached to the piston and the base of the inner tube. Oil fills the inner tube and surrounds its outer surface to a level which allows a free space or reservoir to exist above it, between the inner and outer tubes. On bump or compression, the piston and rod move downwards in the cylinder, resulting in a small pressure drop in the chamber labeled A above the piston. At the same time, the volume of the chamber labeled B below the piston is reduced, causing a high fluid pressure. This unseats the piston intake valve, and fluid flows up through the outer passages in the piston and into chamber A. But the piston rod is also now entering A and displacing a quantity of fluid equal to its volume, so all of the oil in B cannot flow into A. The displaced fluid is forced down through a base valve and out into the reservoir labeled C. In the rebound or extension phase, the piston and rod move upwards and the volume of chamber A is reduced. Chamber A becomes a high-pressure area, and fluid flows through the extension valve in the piston into chamber B. However, the withdrawal of the piston from B greatly increases its volume, and fluid flow from A is insufficient to fill the space. Pressure in B falls below that of the reservoir, causing the base intake valve to be unseated. Fluid flows from the reservoir into chamber B, keeping the inner tube full. The valve provides control over the amount of force required to pass fluid through them at any given piston velocity. They can be made to open in stages, according to fluid pressure. This allows light resistance to motion when the piston moves slowly, and heavy resistance when piston velocity is high. The rapid movement of the piston, continually forcing the oil backwards and forwards through the valves, causes it to heat up, as it absorbs the energy of motion of the spring and converts it into heat. The heat is transferred through the outer tube to the outside air. However, the hotter the oil becomes, the greater its tendency to aerate. Aeration occurs because of the high velocity of the oil as it passes through the small passages in the valves. If the velocity is high enough, air dissolved in the oil comes out of the solution as small bubbles and forms a foam. Aerated oil has a certain amount of compressibility, so it is unable to provide the dampening force previously achieved in the non-aerated condition. The performance of the shock absorber is thus considerably reduced. This effect is called shock absorber fade.
All moving parts in an engine require lubrication. That is, the application of oil to moving parts to reduce friction between them. A lubrication system distributes oil through the engine. A typical lubrication system consists of an oil sump, an oil pump, and oil galleries. The oil is stored in the sump, bolted to the bottom of the engine block. Oil is drawn from the sump by an oil pump. Oil galleries are small passages in the cylinder block that direct oil to the moving parts. Oil that has been pumped to the crankshaft main bearings travels through oilways to the connecting rods. Oil may also be splashed from the connecting rods onto the cylinder walls. A filter is usually provided to remove particles of dirt from the oil, and the circulation of the oil assists with the cooling of the internal parts.
Under the OBD2 standard, the vehicle's computer monitors the emission systems in two ways. The first is referred to as continuous, where major emission-causing faults, such as engine misfire and incorrect air-fuel mix, are continually monitored. The second is referred to as non-continuous. This is where checks are made only once each warm-up cycle. Each time the engine is started, the computer checks components such as the oxygen sensor, catalytic converter, and other engine systems are functioning correctly. If a fault is detected, the malfunction indicator lamp is illuminated, indicating that the vehicle needs attention. If the condition is intermittent and the faulty system operates normally, the MIL will turn off after the vehicle is operated through 3 warm-up cycles, but the diagnostic trouble code will remain in the computer memory for a set period. If the fault does not reoccur within 40 drive cycles, the code will be automatically erased, but will remain logged in the computer memory as a history code.
One function of a lubrication system is to reduce friction. Friction occurs between all surfaces in contact. When moving surfaces come together, friction tends to slow them down. Sometimes that's just what's wanted. Friction can be useful. But it can also cause serious damage. It can make metal parts so hot they melt and fuse together. When that happens, an engine is said to have seized. How long an engine lasts depends to a large extent on how well it's lubricated, especially at the points of extreme loading. So lubrication reduces unwanted friction and controls it where it is useful. It reduces wear on moving parts. Clearances fill with oil so that engine parts move or float on layers of oil instead of directly on each other. Much less power is needed to move them, and that's a plus. It helps cool an engine. It collects heat from the engine, then returns it to the sump, where it is cooled. It helps absorb shock loads. A power stroke can suddenly put as much as 2 tons force on main bearings. Layers of oil cushion this loading. Oil is also a cleaning agent. It collects particles of metal and carbon and carries them back to the sump. Larger pieces fall to the bottom. Oil pumps may be driven from the camshaft or the crankshaft. In a rotor-type oil pump, an inner rotor drives an outer one. As they turn, the volume between them increases. This larger volume lowers the pressure at the pump inlet. Outside atmospheric pressure is then higher. This forces oil into the pump, and it fills the spaces between the rotor lobes. As the lobes of the inner rotor move into the spaces in the outer rotor, oil is squeezed out through the outlet. The crescent pump uses a similar principle. It is mounted on the front of the cylinder block. The inner gear is on the end of the crankshaft, which then drives the pump directly. An external toothed gear meshes with this inner one. Some gear teeth are meshed, but others are separated by the crescent-shaped part of the pump housing. The increasing volume between gear teeth causes pressure to fall. Oil is then taken through the intake port and carried around between the gears and crescent, then discharged to the outlet port. Similarly, in a geared oil pump, the driving gear meshes with a second gear. As both gears turn, their teeth separate, creating a low-pressure area. Higher atmospheric pressure outside forces oil up into the inlet. The spaces between the teeth fill with oil. The gears rotate and carry oil around the chamber. The teeth mesh again, and oil is forced from the outlet toward the oil filter. In a series circuit, components are connected like links in a chain. If any link fails, current to all the components is cut off. In a parallel circuit, all components are connected directly to the voltage supply. If any connection or component fails in a parallel circuit, current continues to flow through the rest. This is one reason why parallel circuits are used in automotive applications like lighting systems. If one lamp fails, current continues to flow through the rest. In a series circuit, all would go out, which could be disastrous. Also, since all components connect directly to the battery terminals, the metal of the vehicle's body can become one of the conductors. One terminal of the battery and one of each component can be connected anywhere on the body or chassis to complete the circuit. This is called an earth or ground connection. It saves a lot of connecting wire. A feature of a parallel circuit is that the voltage across each component is the same as battery voltage. No matter how many components are added or removed, as long as they're in parallel, the voltage across them will be the same as across each other component, including the battery. Another feature of a parallel circuit is that the current flowing in each branch is determined by the resistance of that branch. For this circuit, the resistances of the bulbs are all equal, so the current flowing in each branch is the same. However, the sum of their individual currents is equal to the total current flowing in the circuit. When the resistances are not equal, then the current divides in accordance with the value of each resistance. But the total current flow is still the sum of the currents flowing in each branch. The PCV valve is usually located next to the valve cover of the engine or in the intake manifold. If you cannot identify it quickly, check with the workshop manual. Switch on the ignition and start the engine. With the engine idling, pinch the hose attached to the PCV valve hard enough to shut off the supply of air through it. If the valve is working correctly, the idle speed should drop enough for you to be able to hear the change. Alternatively, remove the hose from the PCV valve attached to the valve cover, leaving the valve in place. And putting your finger over the opening of the hose, you should feel suction. Remove the hose and check that it is still pliable and not clogged with sludgy deposits. If the hose cannot be cleaned easily by blowing some air through it, then it should be replaced. Remove the PCV valve and inspect it for deposits. If it can be taken apart, then you can clean it with PCV solvent or lacquer thinners. If it cannot be dismantled, but has restricted operation because of sludge, then replace it with a new one of the same type. Most automatic transmissions use epicyclic or planetary gears. They are constantly in mesh with each other. A basic planetary gear set has a sun gear, which meshes with planet gears, also called planet pinions. The planet pinions in sets of 3 or more rotate on bearings, on hardened steel pins on a planet carrier, which spaces the pinions equally around the sun gear. It also locates them so they can mesh with an internally toothed ring gear. This means the planet pinions are always in mesh with the sun gear and the ring gear. In operation, their motion is described as either walking or idling. Walking means that if either the sun gear or the ring gear is held stationary, the alternate driving member rotates the planet gears on their pins. This turns the planet carrier in the same direction as the driving member. Planet gears always turn in the same direction on their pins as planet carrier rotation. while they walk around a stationary sun gear. They always turn in the opposite direction on their pins while walking inside a stationary ring gear. Idling refers to the rotation of the planet gears on their pins whenever the planet carrier is stationary. Torque is transmitted from the sun gear to the ring gear, or from the ring gear to the sun gear via the planet gears and the stationary carrier. In both cases, the driven member is turned in the opposite direction to the driving member. To provide the ratios available from the gear set, one or more of the components must be held or released. This is normally done by hydraulic servos, operated by transmission fluid under pressure, acting on lined bands or clutches, or by one-way clutches. They allow turning in one direction, but act as a lockup or reaction member in the opposite direction. In practice, a combination of these is normally used. The rack and pinion steering gearbox has a pinion connected to the steering column. This pinion runs in mesh with a rack that is connected to the steering tie rods. This gives more direct operation. Both the pinion and the rack teeth are helical gears. Helical gearing gives smoother and quieter operation for the driver. Turning the steering wheel rotates the pinion and moves the rack from side to side. Ball joints at the end of the rack locate the tie rods and allow movement in the steering and suspension. Mechanical advantage is gained by the reduction ratio. The value of this ratio depends on the size of the pinion. A small pinion gives light steering, but it requires many turns of the steering wheel to travel from lock to lock. A large pinion means the number of turns of the steering column is reduced, but the steering is heavier to turn. Ratios vary, depending on the type of vehicle. But in each case, the ratio is the same for all positions of the wheels. It is a fixed ratio. The steering rack is supported at the pinion end by being sandwiched between the pinion and a spring-loaded rack guide yoke. This spring-loaded yoke ensures free play is eliminated between the gears, while still allowing for relative movement. The rack is supported at the other end of the rack housing or tube by a bush, normally of nylon. Nylon is used because it has a low coefficient of friction and low wear rate. The pinion is supported by two bearings in the rack housing. These bearings are preloaded to keep the pinion in the correct position, relative to the rack, and to eliminate free play. The rack and pinion steering box is normally lubricated by grease. Each end of the rack is protected from dirt and water by a flexible synthetic rubber bellows, attached to the rack housing and to the tie rod. The bellows extends and collapses as the tie rods move away from and towards the housing as the rack moves. On some vehicles, both bellows are interconnected by a tube, so that as the steering wheel is moved from side to side, air is transferred from the collapsing bellows side to the expanding bellows side. Rack and pinion type steering gears are used because their construction makes them compact and lightweight. Their steering response is very sharp because the rack operates directly on the steering knuckle, and there is very little sliding and rotation resistance, which gives lighter operation.
If a coolant boils, it can be as serious for an engine as having it freeze. Boiling coolant in the water jacket becomes a vapour. No liquid is left in contact with the cylinder walls or head. Heat transfer by conduction stops, heat builds up, and that can cause serious damage. One way to prevent this is with a radiator pressure cap that uses pressure to change the temperature at which water boils. As coolant temperature rises, the coolant expands, and pressure in the radiator rises. It soon rises above atmospheric pressure, and that lifts the boiling point of the water. Engine temperature keeps rising, and the coolant expands further. Pressure builds against a spring-loaded valve in the radiator cap until at a preset pressure the valve opens. In a recovery system, the hot coolant flows out into an overflow container. As the engine cools, coolant contracts and pressure in the radiator drops. Atmospheric pressure in the overflow container then opens a second valve, a vacuum vent valve, and overflow coolant flows back into the radiator. And that stops atmospheric pressure collapsing the radiator hoses.
Locate the adjustment fastener and loosen it. This is usually on the alternator mounting or on a separate pulley wheel. Move the adjusting mechanism in far enough to allow you to remove the belt. Some vehicles use an automatic spring tension system. In that case, pull the tensioning device back so that you can remove the belt. Check the drive and pulley wheels. Look for cracks and other forms of damage. Check that there is no sideways movement indicating worn bearings, and spin the pulley wheels by hand to check that the bearings are rotating freely. Obtain the correct size and type of replacement belt specified in the workshop manual, and compare it with the belt you have just removed. They should be very similar, although the old belt may have stretched in use. Install the new belt, making sure that it is properly seated in the V-shaped groove or the multiple grooves in the pulley, depending on its construction. If the belt is a serpentine type, then make sure that it is the correct width and squarely aligned in the pulley grooves. If it is not correctly aligned, the belt will be thrown off the pulley wheels. Tension the belt using a wrench and a pry bar. Then check it with a tension gauge. With automatic tension systems, gently allow this to apply the tension to the belt. Start the engine and observe the belt to make sure that it is properly seated and operating correctly. Stop the engine again and recheck the tension. Refer to the Vehicle Service Manual to identify the location and type of fuel filter, and the correct procedure for removing and replacing it. If the engine is fitted with an electric fuel pump, locate the fuel pump fuse using the service manual and remove it. Start the engine and wait for it to stop as it runs out of fuel. Switch the ignition off. Obtain the correct replacement filter and components. If the vehicle has a carbureted fuel system, new intake and outlet hoses may have been supplied with the filter. If so, then attach them to the new filter before you disconnect the old one. Loosen the clamps on the fuel line on the engine side of the filter, at the outer end of the hose, and disconnect it. If necessary, drain any excess fuel into the fuel-proof container. Connect the new filter hose and tighten the clamp. Make sure that you have the filter facing in the right direction, with the flow indicator arrow pointing towards the engine. Then remove the old filter and reconnect the new one to the fuel intake. If you do this quickly, very little of the residual fuel in the line should leak from the system. In a fuel-injected system, the fuel is under greater pressure, so the fuel lines are normally made of metal, which are not replaced at the same time as the filter. Using the correct tool, loosen the metal line connectors and remove the filter, catching any leaking fuel in a fuel-proof container. Connect the new filter and tighten the line connectors. Make sure that you have the filter facing in the right direction, with the flow indicator arrow pointing towards the engine. Finally, remember to replace the fuel pump fuse.
Before working on a vehicle's brakes, attach an appropriate label to the vehicle to prevent accidental actuation of the brake caliper while it is removed from the hub. Safely raise the vehicle and remove the wheel. Remove the brake pads and caliper, making sure the caliper is located safely away from the rotor. Remove the rotor by unbolting the securing device and sliding it away from the wheel hub. Before installing the new rotor, clean it thoroughly in a component washer to remove any storage preservative agents. Clean any dirt, rust, and debris from the hub mating surface. Secure the rotor to the hub and rotate it by hand to ensure it rotates freely. Refit the brake caliper and disc pads. Apply the brakes several times to readjust the caliper pistons. Refit the road wheel and safely lower the vehicle. Ask your supervisor to check the brake system pedal pressure, fluid levels, and visual signs of leaks. When the supervisor is satisfied, the vehicle should be road tested by a qualified person to ensure the integrity of the braking system.
Before removing an oil filter, first refer to the service manual for the vehicle and identify the type of filter required. Make sure that a suitable filter will be available as a replacement. The filter will usually be located on the side of the engine block or at an angle underneath the engine. Some filters have a retaining nut which will require a box wrench to remove it. But most late model vehicles have filters which are threaded cartridges. These are removed with an adjustable filter wrench. Remove the filter and clean the seating area on the engine so that its surface and the surface of the new filter can seal properly. Make sure that the seal from the removed filter is not still stuck to the engine. Confirm the correct part number and obtain the replacement filter from your spare parts supply. It is good practice to fit a new filter every time you drain the sump. Smear a little oil or grease on the surface of the new sealing ring. This will help to make a tight seal, but it will also prevent the gasket from binding and distorting while it is being tightened. Screw in the filter until the two surfaces are touching. To help judge the correct degree of the turn, make a mark on the outside of the filter with a pencil or even a dab of oil. But remember to wipe the oil off again when you have finished. Do not over-tighten the filter. Typically, 3/4 of a full turn is adequate torque for a seal that will not leak. Loosen the lug or wheel nuts while the vehicle is still on the ground and raise the vehicle to a comfortable working position. Consult owner's manual for the recommended rotation sequence and check and compare the type of tire fitted with the original specification. If the original wheels and tires have been changed for aftermarket replacements, locate the recommendations for wheel rotation according to the aftermarket manufacturer. Check to see that radial tires are not mixed with bias tires on the vehicle. If there is a mixture, the bias tires should be installed on the front and the radials on the rear. Note that some vehicles have smaller sized tires on the front, and these must not be rotated to the rear. Normally, the wheels and tires are rotated by moving front tires to the rear and the rear to the front. However, in some arrangements they are moved diagonally, so the procedure should only be carried out in accordance with the vehicle shop manual, owner's manual, or the type of tire fitted. Refit the wheels. Screw on the wheel nuts or studs. It is a good practice to put them on finger-tight first, before tightening further. Do not put the nut or stud into the socket of an impact wrench and power them on directly. This practice can lead to the wheel nuts or studs going on cross-threaded. Once the nuts or studs are ready to be torqued down, refer to the shop manual for the correct torque and tightening sequence. Typically, the lug nuts are tightened in a diagonal sequence on 4 stud wheels and in a star arrangement for 5 stud wheels until all the nuts are tight. However, there are exceptions, so the manufacturer's recommendations should be referred to. This should be done to a specification of 50% of the recommended torque for the first stage and then to 100% of the specification at the second stage, using the same tightening sequence for the particular wheel. Open your screw extractor set and study the instructions which should be enclosed. Identify and select the correct size drill and screw extractor for the job. With a center punch, mark the exact center of the broken screw to get the power drill started. Drill a hole through the center of the bolt. Drill only to the depth specified in your screw extractor instructions. Make sure you use the correct screw extractor, that is, the one that matches the drill bit you used. Because the screw extractor has reverse threads, you will need to remember to turn it counterclockwise. Use a tap wrench and turn the screw extractor into the hole. The reverse threads will force the extractor into the hole until the broken bolt or stud is forced to turn. Continue turning until the stud is removed. First, make sure that the gas flow from both the oxygen and the acetylene cylinders is turned off tightly. The 2 cylinders are secured in an upright position. This is usually on a wheeled trolley. Look at the hose pressure and cylinder pressure gauges on top of each cylinder. Both gauges on each cylinder should read 0. If both gauges do not read 0, turn the main cylinder valve on the top of the cylinder clockwise to close it completely. Then you must purge the system of any gas. To purge the system, make sure the main cylinder valve is closed tightly. Pick up the torch handle and note that it has 2 hoses attached. One hose supplies acetylene, the other oxygen. Turn the oxygen regulator under the gauges clockwise and open the oxygen valve on the handle. This will purge any gas that may still be in the system, and the gauges should both drop back to 0. Repeat this procedure with the acetylene cylinder. The torch handle is the connection between the hoses and the working tips. It consists of a body and 2 taps. It's used for both welding and heating. Different attachments are connected to the handle to enable welding, heating, or cutting. Examine the connections. One connection is marked OX and is for the oxygen hose. The other is marked AC and is for the acetylene hose. As a further safety precaution, you'll find the oxygen connector is right-hand thread, and the acetylene connector is a left-hand thread. Welding tips come in sizes that are stamped with a number. Number 1 is the smallest tip. The larger the number, the larger the tip and the greater the heat that it will provide. Select the tip size suitable for the heating task and screw it onto the end of the torch handle. Hold the torch handle in your hand so that you can comfortably adjust the oxygen and acetylene taps. Position the tip so that it faces away from you. Gently tighten the tip securing fitting. You are now ready to adjust the gas pressure for heating. Look at the 2 valves on the torch handle. The valve next to the oxygen hose controls the flow of oxygen to the tip. Close it tightly clockwise. The valve next to the acetylene hose controls the flow of acetylene to the tip. Also, close it tightly clockwise. Now that you're ready to use the torch, turn the main valve on the top of each cylinder counterclockwise half a turn to open the valve. The needle on the cylinder pressure gauge will rise to show you the pressure in the cylinder. Turn the oxygen regulator handle clockwise until the needle in the gauge registers 10 psi. Turn the acetylene regulator handle clockwise until the needle in the gauge registers 5 psi. This is your working pressure for heating. Before you light the torch, check the area you're working in to make sure there are no flammable materials or fluids nearby. Workmates should also be clear of the area. The welding flame is not only extremely hot, it also produces dangerous ultraviolet rays, which will damage your eyes. It is absolutely vital that you are wearing the right safety gear, gloves and tinted goggles or face mask. So put them on and adjust them comfortably. Now you are ready to ignite the torch with the striker. The tip of the torch must be pointing downwards away from your body and away from the gas cylinders. Turn the acetylene valve on the torch handle slightly towards the on position. You should hear the gas hissing. Hold the striker against the tip of the torch with the lighter cup between the torch and you. Flick the striker to create the spark that will ignite the gas at the tip of the torch. Open the acetylene valve slowly until the sooty smoke produced by the torch disappears. Then slowly open the oxygen valve on the torch handle. As you open the oxygen valve, you will see the color of the flame change. The pure acetylene flame is yellow, and it will change to blue as you add the oxygen. Continue to open the oxygen valve until you can observe a small, sharp blue cone in the center of the torch flame. This is the neutral flame you need for general heating. Most light vehicles use a single plate clutch to transmit torque from the engine to the transmission input shaft. The flywheel is the clutch driving member. The clutch unit is mounted on the flywheel's machined rear face, so that the unit rotates with the flywheel. The clutch unit consists of a friction-type disc with 2 friction facings and a central splined hub, a pressure plate assembly consisting of a pressed steel cover, a pressure plate with a machined flat face, and a segmented diaphragm spring, and a release bearing and operating fork. The friction disc is sandwiched between the machined surfaces of the flywheel and the pressure plate when the pressure plate is bolted to the outer edge of the flywheel face. The clamping force on the friction facings is provided by the diaphragm spring. Unloaded, it is a dished shape. As the pressure plate cover tightens, it pivots on its fulcrum rings and flattens out to exert a force on the pressure plate and the facings. The transmission input shaft passes through the center of the pressure plate. Its parallel splines engage with the internal splines of the central hub on the friction disc. With engine rotation, torque can now be transmitted from the flywheel through the friction disc to the central hub and to the transmission. When the clutch pedal is depressed, the movement is transferred through the operating mechanism to the operating fork and the release bearing. The release bearing moves forward and pushes the center of the diaphragm spring towards the flywheel. The diaphragm pivots on its fulcrum rings, causing the outer edge to move in the opposite direction and act on the pressure plate retraction clips. The pressure plate disengages and drive is no longer transmitted. Releasing the pedal allows the diaphragm to reapply its clamping force and engage the clutch, and drive is restored.
The spark plug consists of a plated metal shell with a ceramic insulator and an electrode extending through the center of the insulator. Threads on the metal shell allow it to be screwed into the cylinder head, and a short earth electrode attached to one side is bent in towards the center electrode. The electrodes are of special alloy wire with a set recommended gap between them. The spark bridges this gap to ignite the air-fuel mixture in the combustion chamber. Spark plugs are identified by 3 different features. These are 1. Thread size or diameter, 2. Reach or length of the thread, 3. Heat range or operating temperature. Spark plugs should operate between average temperatures of around 750 to 1500 degrees Fahrenheit or 400 to 800 degrees Celsius. This is referred to as the heat range. The temperature that a spark plug will reach depends on the distance the heat must travel from the insulator to reach the outer shell of the plug and enter the cylinder head and water jacket. If the heat path is long, the plug will retain more heat and therefore will run at a higher temperature than one with a short heat path.
Applying a force to this object deforms it. Removing the force lets it return to its original shape. This characteristic is called elasticity. Automotive suspension systems generally use the elastic properties of metals to provide the springing medium. The springs are located between the frame and the axle assemblies and are shaped to suit the application. Leaf springs are normally semi-elliptical and they absorb the applied force by flattening out under load. Coil springs are formed in a spiral from a single steel rod and absorb the force of impact by twisting. Torsion bars are held rigid at one end and twist around their center as the suspension arm is deflected. They all return to their original shape when the deflecting force is removed. Non-metallic materials like rubber can provide the main springing action, but are more commonly used as stops to limit extreme suspension movement. The stops can also be shaped to provide an auxiliary springing function. In light vehicle applications, air is normally used only for ride height control. When a vehicle strikes an uneven surface, the springs are deformed from their original shape. They return to their original position, but tend to overshoot and set up oscillations. This makes the vehicle bounce up and down, which makes the ride uncomfortable. It can produce forces that make the tyres bounce, and a bouncing tyre won't grip the road surface well. Shock absorbers have a marked effect on how well tyres follow a road surface. They damp the natural bounce over the road and reduce spring oscillations. There are different kinds of shock absorbers, but they all use a piston sliding in a cylinder filled with oil. The dampening action occurs as a result of the piston movement forcing the oil through valves in the piston and at the foot of the shock absorber, which restricts oil flow. The oil heats up from this continuous movement as the energy of motion of the suspension is transformed into heat. This heat is transferred through the body of the shock absorber to the outside air.
Switch on the ignition. The charge light on the dash should light up and go out when you start the engine. This indicates that the alternator is charging the battery. Turn the engine off. Switch on the headlights of the vehicle, then start the engine and see if the lights brighten significantly. If they do, then this indicates that the alternator is charging the battery more than it is being drained by the lights. If you do not have someone else to start the engine for you, judge the brightness by shining the lights onto a reflective surface such as a wall. Check that the battery casing and the terminals are in good condition.
This can generally be achieved just with a visual inspection. However, since the battery may be located in a position where you cannot see all of it, you may have to remove it to complete the inspection, after performing any other on-car tests. A sealed or low-maintenance battery has no removable cell covers, so you cannot adjust or test the fluid levels inside. However, some of these do have visual indicators that provide information on the status of the charge and condition of the battery cells. Each manufacturer provides details of these visual indicators, so refer to these when undertaking an inspection. If the battery is not a sealed unit, it will have removable caps or bars on top. Remove them and look inside to check the level of the battery fluid, which is called the electrolyte. If the level is below the tops of the plates and their separators inside, add distilled water or water with a low mineral content until it just covers them. Be careful not to overfill the cells, as they could boil over when charging. Test the specific gravity of each of the cells by using a hydrometer designed for battery testing. Draw some of the electrolyte into the tester and look at the float inside it. A scale indicates the relative charge state of the battery by measuring how high the float sits in relation to the fluid level. A very low overall reading of 1150 or below indicates a low state of charge. A high overall reading of about 1300 indicates a high state of charge. The reading from each cell should be the same. If one or two cells are very different from the rest, that indicates there is something wrong with the battery. Select the volts DC position on your DVOM and attach the probes to the battery terminals, red to positive and black to negative. With all vehicle accessories switched off and the battery at 70 degrees Fahrenheit or 21 degrees Celsius, the voltage reading should be 12.6 volts if the battery is fully charged. This will be slightly lower at cooler temperatures. Measure the continuous load capability of the battery with a load tester. Refer to the manual of the particular tester for its operating instructions. A load tester induces a high rate of discharge in the battery, like the load created by a cranking starter motor. A battery is rated in ampere hours, which means that it can supply a certain number of amperes for a specified length of time under continuous load. Another measurement used is International Standard Cold Cranking Amps. Check the specifications for the battery you are testing. If it can meet these specifications under a load test, then it is in good condition. There are different makes and types of load testers. Always use the equipment manufacturer's recommended testing procedure.
Read the safety instructions that are provided with the hoist. They should be displayed near the lift operating controls. Check the hydraulic system for leaks. Make sure there are no oil spills around or under the hoist. The hoist should be completely down before you attempt to drive the vehicle onto it. You should also check the arms and pads for any signs of damage. Check under the vehicle to make sure there are no parts which will interfere with the hoist operation and that the vehicle is structurally sound and not badly corroded. Check the vehicle service manual or your workshop service manual and locate the correct contact points for the lifting pads. Carefully drive the vehicle onto the hoist and position it centrally. Leave the vehicle in neutral with the emergency brake off. You may need to move the car forward or backward to allow the arms to swing under the car. Position the lifting pads under the vehicle lifting points.
make sure the lifting pads are adjusted to the same height for both sides of the vehicle. Move to the operating controls and raise the hoist just far enough to come into contact with the vehicle. Make sure that the lifting pads are positioned centrally under the contact points. Make sure nobody is near the vehicle, and then raise it just far enough for the wheels to be off the floor. Check the position of the lifting pads to make sure they have not moved, and shake the vehicle gently to confirm that it is stable on the hoist. Once you are sure the vehicle is safely positioned on the hoist, lift it to the working height. With the vehicle at the correct height, you should now lock the hoist in place and engage whatever safety device is used with it. Before the hoist is lowered, remove all tools and equipment from the hoist area and wipe up any spilled fluids. Remove the safety device or unlock the lift before lowering it. Make sure nobody is near the vehicle on the hoist before lowering it. Once the vehicle is on the ground, you can remove the lifting arms and drive it away from the hoist. Position the vehicle on a flat, solid surface. Put the vehicle into first gear or park, and set the emergency brake. Then place blocks in front of and behind the wheels that aren't going to be raised off the ground. Before you try to use the jack, check for leaks in the hydraulic system. Check the pad or saddle and the wheels of the jack. They should rotate freely and show no signs of damage. Check the manufacturer's label on the jack. The specifications will tell you the maximum load weight it will bear, so it must suit the vehicle you want to raise. Refer to the owner's manual to find out where you can safely place the jack. This is usually a major point on the chassis, a cross member or axle unit. Before operating the jack, select two safety stands of the same type, suitable for the weight of the vehicle. Check the stands for any cracks, and if necessary, lubricate the threaded adjusting post with a few drops of engine oil. Place one stand on each side of the vehicle at the same point. Adjust them so that they are both the same height, and high enough to slip under the vehicle once you've raised it. Roll the jack under the vehicle, and make sure the pad or saddle is positioned correctly under the frame or cross member. Turn the valve on the top of the jack handle clockwise, and begin pumping the handle up and down until the jack pad touches and begins to lift the vehicle. Once the wheels lift off the floor, stop and check the placement of the jack pad under the vehicle to make sure there's no danger of slipping. Double-check the position of the wheel blocks to make sure they haven't moved. If the vehicle is stable, continue lifting it until it's at the height where you can safely work under it. Slide the two jack safety stands underneath the vehicle. Make sure they're positioned at a point that can support the weight. Both stands should be adjusted to the same height and placed as far apart as practical. Turn the valve on the jack handle counterclockwise and gently lower the vehicle onto the stands. When the vehicle has settled onto the stands, lower the jack completely and remove it from under the vehicle. Repeat this process to lift the other end of the vehicle. Be aware that the vehicle is now supported on jack stands and will not be as stable as it would be if the wheels were on the ground. When you've finished working under the vehicle, make sure you've removed all tools and equipment before you attempt to lower it. Use the jack to raise the vehicle off the safety stands. Slide out the safety stands from under the vehicle. Turn the valve on the jack handle counterclockwise very gently to lower the vehicle to the ground. Do not allow the vehicle to drop quickly, or you may cause serious damage. Return the floor jack, the safety stands, and the wheel wedges to their storage area before you continue working on the vehicle. The water pump is usually in front of the cylinder block, belt-driven from a pulley on the front of the crankshaft. A hose connects it to the bottom of the radiator where the cooler liquid emerges. It has fan-like blades on a rotor or impeller. Coolant enters the center of the pump. The rotor spins and centrifugal force moves the liquid outward. It is driven through the outlet into the cooling passages called water jackets. Water jackets are passages in the engine block and cylinder head that surround the cylinders, valves, and ports. Coolant can be also directed to hot spots, such as the exhaust ports in the cylinder head, to stop local overheating. Finally, hot coolant is ready to leave the engine.